Alrighty, welcome to Chapter 4, Systems and Matrices. So we're going to be talking about systems and matrices this chapter. Probably one of my most favorite chapters because it's so applicable to real life. And it's going to be fun. There's a lot of different things we're going to talk about that are really entertaining. So let's first start off with the systems. So we're going to start 4.1 with systems of linear equations in two variables. Now remember, a linear equation in two variable is just that 2x plus 3y equals 6. So don't think we're starting over with something brand new. We're just building on what we learned last time. Alrighty. But you may be wondering, okay, I know what linear equations are, but what is a system? What is a system? A system just means two or more. So 2 plus equations, that's all it means. So I have two or more equations that are working together and where the x's and the y's are the same number. That's really all I'm working with. So it's just two or more. Let's take a look at this solution, or this system of equations here. We can start talking about solutions to these guys. So here we've got, below is the graph of two types of cameras being sold. One is a digital camera, and the other is film. I know there's really no film cameras anymore, but let's just pretend there is, okay? The graph of the the graph shows the sales for both over a span of 6 years. So here we've got two different things going on. We've got two different lines, two different equations, but the same x's and the same y's, right? So the x's still represent those years. Oops, so sorry. Years. And those y's represent the sales, the money. And of course, we want to double check the sales are definitely in billions. So it's sales in billions. So here the x's and the y's represent the same concept, right? We just got two different situations. One for film and one for digital. Now a solution to this system of equations, this would be where they intersect, right? It would be where they share a solution. Remember, if you recall from the last chapter, that we can put it down here, a solution to an equation is an ordered pair that works, right? Is an ordered pair. Oops, sorry, not order pair, ordered pair that satisfies the equation, that works for the equation. And so a solution to a system works for both. Solution to a system works for both. Alright, so a solution to just one equation, any ordered pair that when you plug it in, it makes sense. A solution to a system, works for both, or all of the equations, I should say, because some systems have three, some systems have four. But the ordered pairs that work for those equations, where they make true statements like 6 equals 6, or x equals x, then those systems have solutions, right? So that's what we're talking about. So let's look back at our little chart up here, our graph. Where would be the solution to this system, an ordered pair that you would find working for both of them? That's right, it'd be right here at their intersection point, right? This point right here works for both the blue line and the orange line, meaning if I were to graph the points on the blue line and graph the points on the orange one, this would be the one they have in common. Let's check out what exactly that point is. We're going to have to guess just a little bit because this graph's not perfect, but it looks like in about 3.5, we'll round, we'll call it 3.5. So 3.5, okay. Sorry about that. 3 and 3.5. At 3.5 comma, well this one's a little easier to read, it goes right on the line 10, right? So they share the point 3.5 comma 10. That's a solution they have in common, right? And what does that mean? That means that at 3.5 years, right, 3.5 years of this measuring, 3.5 years, they both had $10 billion in sales, right? So 3.5, at 3.5 years, they both had $10 billion in savings, or in sales, pardon me. I wish we had $10 billion in savings, right? Now, it's 3.5 years, they both had $10 billion, and that's the key word right there, both. Both had $10 billion. That's their solution, their common solution. Alrighty. Now, not always is it going to be presented as a graph to you. Instead, most often, it's going to be presented as a system of lines. So when we look at these equations, right, the blue line, I'm sorry, on yours it's probably, they're both black, but the negative slope line has an equation of negative 1.7x plus y equals 4.4. And the orange one has 2.5x plus y equals 19.4. So we could solve this geometrically like we just did, find out where they cross. And, or we could solve this a whole bunch of other ways. But basically what we're looking for is that ordered pair that they share, right? That ordered pair that is in common. That is the solution to this system. Let's check out some other systems. So down here in example 1.1, we've got this ordered pair here, 4, 2. And we need to see if it is an actual solution to this system. And if it is, what would happen? What would happen to this system? Well, how would we check that this is actually a solution? Go ahead and pause the video now and talk about it. Okay, so maybe we had a chance to discuss it, but an ordered pair, in order for it to be a solution, must actually work for both equations, right? So what we would do is take this and plug it in. Let's go ahead and do that. So we have this first equation. We'll do it in pink or orange. This first equation is x plus y equals 6. So I'll take this ordered pair, this x comma y, right, and I'll go ahead and plug it in. Does 4 for x and 2 for y. Does that actually equal 6 like it's supposed to? Yes, it does. Check. It does. Okay, so check on the first one. That's awesome. If this was just a single equation, then we can say, yes, this is definitely a solution. However, it's a system, right? It's a system where these two work together. So we also want to check the other equation. We have to check both. All right, so in this other equation, we have 4x minus y equals 14. So I'll check this same point. 4 times, let's see, what am I replacing with x? I'm replacing it with 4. 4 times 4 minus, instead of y, all right, 2 should equal 14, but let's go ahead and solve that. Let's solve that. 4 times 4 is 16. Minus 2 would be 14. Is that what we were supposed to get? Yes. So this is also true. Therefore, yes, this isn't, since it satisfied both equations, right? Both equations, then we know that this, in fact, is a solution. And sometimes I'll abbreviate solution like that. So it is a solution because it satisfies both those equations. Alright, go ahead and pause the video now and test out this other point. We've got problem B here, negative 1, 7. Is that a solution to this system? Is that a solution to this system here? Alrighty. Hopefully you had a chance to try this on your own. We're going to try it out real fast. So this first equation, call it the orange equation, 3x plus 2y equals 11. Let's plug in our point and see what we get. Instead of x, we'll do 3 times negative 1 plus 2 times 7. Plus 2 times 7, right? I'm plugging into my point, plugging my point in. That should equal 11. That should be the case. Let's see if it actually is true. So we get negative 3 plus 14. And yes, it does, in fact, 11 equals 11. That is a true statement. So yes, that one works. Let's check the other one out as well. I've got x plus 5y equals 36. So I'll plug in negative 1 plus 5 times 7 equals 36. All right, negative 1 plus 35 equals 36. I don't know about that, but that says 34 equals 36. Is that true? No, that's definitely not. So all of these would be not equal to. This one fails. So what can we do if only one fails and one is true? Does that mean it's a solution? No, it's an all or nothing game. So this is not a solution. It has to work for both, right? In other words, what we have here, we were somewhere back up here, we have the point that's kind of over here. It works for one, but doesn't work for the other. And we are only interested in things that are common solutions, right? So if it's not common, then it's not a solution to the system. So this is not a solution. Alrighty. So the next thing we're going to talk about is instead of being given a point, we're actually going to go start finding these points ourselves. Now the easiest way, or not the easiest way, but the most straightforward way is to graph them and see where they intersect, just like we did with the very first thing. So we're going to start by graphing two systems, or sorry, graphing a system, which means graphing two or more equations, right? As always, we have steps listed, and you are more than welcome to read these and use them during your homework, but for now we're just going to do it together and save ourselves some time that way. I have no idea why this happens. Whenever I try to upload a systems problem, it likes to mess up the spacing all over the place, so hopefully yours is still a system, one under the other, as you will often see. I will have to double check later on other things that might have been messed up, but hopefully yours is still in order. If not, then just remember, you can just rewrite it like I am. So my system is x plus y equals 5, and 2x minus y equals 4. So that's actually my system. Sometimes you may even see a curly bracket around it to indicate that they are, in fact, two equations together. That is a system. Not often, though. Let's go ahead and try and solve this by graphing. So what do you think? How do you solve this by graphing? Well, we're going to need to graph these two and find their solution. Let's go ahead and do that. Let's start with this first one. We'll make it green. I really like to use colors when it comes to these guys because it helps me keep my thoughts straight, which one I'm working with, whether I've graphed it or not, or worked with it or not. If you don't like colors, it's totally fine, but I will be using lots and lots of colors. So x plus y equals 5. From the last couple chapters, we saw there's multiple ways to graph this guy. I think we're going to go with the easiest one. We're going to switch it into slope-intercept form, and then graph it using y equals mx plus b. So let's go ahead and do that. Subtract x to both sides. Get y is equal to negative x plus 5, or negative 1x plus 5, right? So that means, so now I've got it in slope-intercept form. My 5 is my y-intercept, which means my y-intercept is 0, 5, right? That's what that translates to. So I'll go up to 5, 0, 1, 2, 3, 1, 2, 3, 4, 5 is like right there up at the top. Wait, right there. Make my box bigger, maybe? Nope. Alright, 1, 2, 3, 4, 5. That'll be my starting point. And then from there I have a slope of negative. Well, slope of negative is the same thing as slope of negative 1, which is a slope of negative 1 over positive 1, right? Not negative 1 over negative 1. This is something I see happening a lot. But it's negative 1 over positive 1. So I'm going to go down 1 and to the right 1. That gives me my negative slope. And I'll go ahead and draw that line. Alright. Okay, that's a horrible line. We're going to erase that just a little bit. Okay. Now with this one, I know in the past I said it doesn't really matter how straight your line is, but if we're trying to find where these two are actually intersecting, it's kind of important where our line would be. Right, how straight our line is. So I'm going to try and make this as straight as I possibly can. But honestly, with a stylus on a phone, not really the most accurate. So we'll try our hardest, right? All right, so that's the graphing of x plus 5 equals, or x plus y equals 5. Now let's graph that other one. You can even work it in pink. So I have 2x plus y, or 2x minus y equals 4. Again, I'm going to solve this for y. So I have 2x minus y equals 4. I'll subtract 2x from both sides. Negative y equals negative 2x plus 4. Write that better. Negative y equals negative 2x plus 4. And then we'll divide that negative part out, or in other words, divide by negative 1, so we get y is equal to 2x minus 4. Alrighty. 2x minus 4 means our y-intercept is at 0, 0, comma, negative 4. So I'll go ahead and go down. So 1, 2, 3, and 4. There, it looks like it's right there. And then a slope of 2 translates to 2 over 1, right? Just like last time, just like when we were plotting these individually. So 2 over 1 says up to and over 1. That gets right there. Alright, now I'm going to try my hardest to draw the straightest line I can. Go 2 over 1, up 2 over 1, 1. There we go. And there we are. There's that line, that pink line of y equals 2x minus 4. Alright, so I have graphed both of these lines onto my graph, the same graph. And what am I looking for here? What am I looking for the answer, right? What is the answer? The answer would be a solution, and I want the solution of this system, so I want where they intersect, the point they have in common, right? Intersect, not intercept. Intersect. That's what I want. I want their intersection point. So clearly that would be right about here. And it actually looks like it ended up being right on a dot for us. That's actually really nice, right where two lines cross. And that looks like the point 1, 2, 3, comma, 1, 2. So the solution is going to be 3, comma, 2. That is the point that they share in common. Righty. If you have any questions at all, please pause now, get them answered. And then we can move on to talk about some other kinds of solutions. Alrighty, now we just saw that normally you end up with one solution, right? With linear lines, with straight lines, you're only going to end up with one common thing, right? One common thing, if that. So in most cases, 9 out of 10 cases, well I should say 8 out of 10 cases because there's two other options, but 8 out of 10 cases you end up with a single point solution. Sometimes you end up with no solutions. We call those parallel lines. So this would have one solution. This would have no solution, right? And that makes sense. If we remember the early definition of parallel lines, they're points that do not cross, or lines, pardon me. They're lines that do not cross. They don't have an intersection point, right? And so, of course, they're not going to have a solution if the solution is supposed to be their intersection point, right? A solution is supposed to be where they intersect. If they don't intersect, they have no solution. So that would be the 1 out of 10 cases. The other 1 out of 10 cases would be where they are the same line. Sometimes you'll see that. Sometimes you'll see things like y equals 2x plus 4 and 2y equals 4x plus 8. And notice, I've just taken the first equation and multiplied everything by 2, right? And so they are actually the same line. That's how you get this one line on the graph. They actually lie over each other, and anywhere along this point, or along this line, they're going to intersect. That would be infinite solutions. Infinite solutions. So if they end up with the same line, they're infinite solutions. If they have the same slope and same y-intercept, infinite solutions. If they have the same slope but different y-intercepts, that's going to be no solution. So those two you have to watch out for. But like I said, 8 out of 10 are going to be more this situation where they do actually cross and they create a single solution for you. Alright, it's solving by substitution. Now, there are two more methods to solving these guys, and they are algebraic methods instead of graphical methods. Instead of geometric, where you actually have to plot it out and see where they have in common, which is never a bad method, but it's not the most efficient, right? It's not the most, it's really time-consuming and not very accurate, right? Here we lucked out and it actually managed to cross at a point of two lines, but sometimes it won't. Sometimes in something like this, I mean, even there, you can see it's halfway in between two lines, and that's not really the easiest, the most accurate to call a solution. So a much more accurate method would either be by substitution, or later on we're going to learn elimination. Either one is acceptable. I do not believe I asked you to solve a certain way, but on your homework you will be asked to solve certain ways. So you have to learn both of these, all three of these actually. So let's start with substitution, solving by substitution. Once again, there will be some steps, but let's look at this problem first. So we've got this system here, this system of two equations, 2x minus y equals 6, and x equals y plus 2. Now basically the idea in substitution, it's just like any other mathematical concept. When they tell you a name, solving by substitution, they are trying to tell you what to do, right? Just like when slope-intercept form, when they were telling you it's the slope and the y-intercept, here they're telling you the method of substitution solves by substituting something. This is what it means. So we are solving by substituting. We are replacing. We're going to replace a variable. Replace a variable with something else. So let's look at the system they gave us. They gave us two equations, right, because it's a system. And we have this one where the variables are on both sides. And then we have this one where the variables are on different sides. It says that x is equal to y plus 2, right? So we've got this x is all by itself. X is alone. When you see stuff like that, it's very, very easy to use substitution because it's already really been solved for you. What I'm going to do is I'm going to take this second equation and I'm going to essentially substitute it into the first one. That's the idea. So I have this x, right? I've got this x, it's x plus, or it's equal to y plus 2. And I'm going to use color so you can kind of see this. So I'm going to take my first equation I'm not going to use that color because that gets rid of the whole purpose I'm trying to do. So hold on one second. So 2 times x, and that x is going to be in pink, just to show you that it's the same x from the second equation, right? And then minus y equals 6, right? So the only thing I've highlighted is the fact that these x's are the same. Now instead of writing it this way, I'm going to write all the red the same, but I'm going to substitute what I know about x. I know that x is equal to y plus 2, right? I know that. That's what that second equation says, that x, no matter what it is equal to y plus 2. So instead of the pink, I'm going to write that blue statement. So I'm going to keep all the other red the same. Right? So I've got 2, I've got negative y, I've got x, or I've got 6, right? All the same. But instead of x, I'm going to write the blue that I know about x. I'm going to write this blue. I'm going to write y plus 2. I know that instead. And that's what they mean by the substitution. I've substituted this pink stuff for this blue stuff. I've substituted the idea of the second equation in for the into the first equation. And because I've done that, now you'll notice that there are no more x's. And when there are no more x's and only y's, I can actually solve. If I have one variable, I can solve. So I'm going to go ahead and do that. Now I'm going to solve this equation. Distribute this guy in. End up with 2y plus 4 minus y equals 6. Got some like terms I can combine, right? I got 3y plus 4 equals 6. Subtract that 4 over, I get 3y is equal to 2. I'm sorry, no I don't, because I subtracted that, so this should just be 1y. Erase the 3. 1y is equal to, so I got y plus 4 is equal to 6. Subtract the 4 over, and I get y is equal to 2. And I have solved for y. Awesome. So y is equal to 2. That's awesome. However, remember, a solution is an ordered pair, so I'm not quite done. First I solved for y, now I'm going to go back and solve for x. You might be thinking, oh my gosh, there's so many parts of this problem, it's going to take forever. Luckily, the second part is like really easy, because I know that x is y plus 2. If I know x is equal to y plus 2, and I know y is 2, let me just plug that in, right? So I just got to plug it in. So if x is equal to y plus 2, and I just found out that y is 2, then x is equal to 2 plus 2, and so x is equal to 4. Oh, look, it took like 10 more seconds to find that x, right? I'm going to write it in a darker color because you guys can't even see any of that. So x is equal to 4, right? All right, so now I found that x is equal to 4, and so my solution, my ordered pair, is going to be 4, 2. And remember, what we just found was where if we were to graph these two lines, that's where they would be intersecting. That's what we have, a solution and intersection point. Awesome. All right, so that was substitution where you take a variable and you replace it in the other equation so that you're just left with one and you can actually solve. Then you go back and you solve for the other one, right? Solve for the other one. All right. Let's try that again, just to get some practice, right? And let's take a look at this guy. What's different about this system compared to the system I just showed you? So talk about that for a sec. Just don't worry about substitution yet, but talk about what's different. What's different? Alrighty, so I hope you said it's because, or they're different because neither one of these is actually solved for a variable, right? They're both standard form. This one has the variables on both sides, so does the second one. However, that doesn't mean we can't do anything, because remember, at any point, we can always rearrange an equation. Every single time, we can always rearrange an equation. So it's really up to us which one we want to solve for. Last time we had x equals. I think I'm going to try a y equals this time because that's totally fine. Notice the method, nothing here says you have to solve for x, you have to solve for y, you have to substitute for x, you have to substitute for y. It doesn't say any of that. It just says you have to substitute for one of them. One of them. So I'm going to take this second equation here, this 4x minus y equals 1. And I'm going to solve it for y, because we're pretty used to that. We're pretty used to solving for y with all those slope-intercept form, right? So let's go ahead and do that. Subtract 4x from both sides, and you get negative y is equal to negative 4x plus 1. Divide by that negative 1, you get y is equal to 4x minus 1. Sweet, we have solved for a variable. Now we can use substitution. We're going to take that we know now that y is equal to this stuff. This stuff. That's what we're going for. That something, one of them, is equal to some sort of expression involving the other. So y is equal to 4x minus 1. In the other one, it was x was equal to y plus 2, right? So 1 is equal to some expression involving the other. Let's go ahead and take that now. We'll substitute it into that first equation. So that first equation says 3x plus 2. We'll use, oops, I just used red. Hold on, let's not use red. Let's use orange. So 3x plus 2, and then y is equal to 13, right? The original equation we have, and since y is equal to, let's use blue, 4x minus 1, I'll take out the red stuff and I'll replace it with the blue stuff. So everything orange stays the same. 3x plus 2, and it still equals 13, but instead of a red y, I'm going to write a blue 4x minus 1. And yes, those parentheses are very important. You must put in the parentheses. Alrighty, now I can solve this one because it's only got x's. The y is gone. That was the whole point. You wanted to get rid of one of them so you could actually solve for the other. So let's go ahead and solve that out. We have 3x plus, distribute, gives us 8x minus 2 equals 13. Those together make 11x minus 2 equals 13. And then you add the 2 over. Did I make a mistake? Was that negative? Yep, it was negative 1 to start. I do apologize. This was negative 1 to start. So this should have been 4x plus 1. Negative 1, so 4x plus 1, which means this blue should have been a plus, which means this 2 should be positive. Sorry about that. Probably wondering why I'm so crazy. Alright, and then we'll subtract the 2 to both sides, and you get 11x equals 11, or x is equal to 1. Alright, now even if that wasn't the case, even if it was still some sort of hideous fraction, that's fine. We'll see some hideous fractions in a sec. But sorry about that. So that x should have been a positive, or sorry, that 1 should have been negative, and therefore it would be positive. Anyway. Alright, so x is equal to 1, and then we eventually have to go back and find out what y is, right? Because this so far is only 1/2 of our coordinate pair, our ordered pair. But that last step's fairly easy to do since we've already solved for a variable, right? We have this y is equal to 4x plus 1. Now I know that x is equal to 1, so y is equal to 4 times 1 plus 1, or it's equal to 5. So the other half would be 5. And there's our common solution, the solution that would work for both of these equations. Alrighty, pause the video now if you have any questions at all. We're going to do one more involving some fractions, and it's only going to get a little more complicated from there, so I encourage you to ask your questions now. Okie dokie. Hope you had time to get your questions answered. We have one last system we're going to solve by substitution here. It's got some fractions in it, but that's okay, right? It doesn't really matter that it has fractions. Remember, fractions are just rational numbers, and so they behave the exact same way with just a few more rules added on. If we need to add some fractions, all right, whatever. But I'm actually going to take this this fraction equation, and that's going to be the one I'm going to solve for, because I'm noticing that these denominators are all factors of each other, right? 3 times 2 equals 6. So I'm wondering if maybe that might work out if I solve for that one. Do I have to solve it that way? Absolutely not. You can solve the second one for one of the other, for x or y, and then plug that in, but you might be dealing with a few more multiplications of fractions. So I'm going to start by solving this first one. Alrighty, and I think I'm going to solve it for y. Let's solve it for y. So I have 2/3 x minus 1/2 y is equal to 7/6. So I'm going to move the 2/3 over. Yeah, I'm going to move the 2/3 over. Do I want to solve it this way? Yeah, I do. Okay. So negative 1/2 y is equal to negative 2/3 x plus 7/6. And then in order to get rid of a negative 1/2, I'm going to times by negative 2. Times everything by negative 2. Okay, whatever. So I have y is equal to times by negative 2. And y is equal to, well, negative 2 times negative 2 over 3 is going to be a positive 4 over 3 x. And then negative 2 times 7 is going to be 14 over 6. Alright, so it didn't work out so much in my favor. I thought it might work out, but it didn't. That's okay. No big deal. It's still solved for y. So I'm going to take this expression, and I'm going to plug it back into the other one. So now I'm going to take my original equation, or my second equation, 3x minus y equals 6, and I'm going to get rid of the y part, right? I'm going to get rid of the y part. So I have 3x minus, now 4/3 x plus 14/6, which actually I can reduce down a little bit, maybe make my life a little easier. Divide both by 2, you get 7 over 3. And that's still equal to 6. So I've replaced that y part with that expression that I just solved for. Alrighty. Now notice I still put the parentheses around there. The reason I had to do that is because now I need to distribute this negative. I must distribute that negative. So 3x minus 4/3 x minus 7/3 equals 6. If you don't do that, you're going to end up with a solution that does not actually work. So watch out. Make sure you just watch out for those common things. Minusing a negative, timesing by 2. You should always pretty much have something to distribute. Alright. So 3 minus 4/3. Well, 3 is equal to 9/3 minus 4/3 minus 7/3 equals 6. And therefore I'm left with 5/3 minus 7/3 equals 6. Scroll up just a little bit. I'll add 7/3 to both sides. So I have 5/3 x equals, let's do that over here. Do this little side thing. 7/3 plus 6. Well, 7/3. Sorry, one sec. Is equal to 7/3 plus, let's see, how many thirds is 6 whole pies? That would be 18/3. So I've unreduced that fraction, right? So 18 divided by 3 would be 6. In other words, 6 is 18 times 3. Add those together, you get 25 over 3, right? So, call that x. 5/3 x is equal to 25 over 3. I'm going to multiply by 3 over 5 to both sides, right? Multiply by the opposite. Looks like that cancels that, and I'm left with just x. Here, looks like the 3's cancel. 25 divided by 5, x equals 5. All right, x equals 5. So even if I had gone the other route, I probably would have had to end up with just as much fraction multiplication and division, adding and subtracting. So if that's sort of a weak area for you, that's kind of why I put this example in there. I want you to be working on that. Fractions will not go away. In fact, we're going to have an entire chapter this year about fractions. So you need to remember your fraction rules. If you don't know them, come swing by tutoring, email me. I will send you other stuff you can do. point out chapters in your book. There's always ways to go and fix that, okay? So you need to buff up on your fractions as well. We're not quite done with this problem because we only have 1/2, right? We have a 5 for our coordinate pair, but we do not have the y value. So how are we going to go find the y value? Well, let's go plug it back in. I could use this equation, but I know you're all mad at me for doing fractions, so why don't we do this equation? Why don't we do the second equation here? Because regardless, it should work in either one, right? Should work in either one. So let's go down here, kind of section it off. 3x minus y equals 6, right? I know x equals 5, so 3 times 5 minus y equals 6. 15 minus y equals 6, or what minus 15 would be 6? Y equals 9. Yes, y equals 9. And so the other half of our solution would be 9. 5 comma 9 is the point that these two share in common. Alright, if you have any questions, make sure you pause. We're going to go talk about elimination now. But substitution is a method you will have to practice on your homework, and it saves you a lot of time if you can identify those things that you can substitute. Alrighty, elimination. I believe, yes. Elimination. Let's talk about elimination. So elimination is our other method. It does not involve substitution. In fact, it involves elimination, right? So once again, it's the name trying to tell you what you're going to be doing. Instead of substituting a value, we will be eliminating a value. Instead of substituting a variable, we will be eliminating a variable. We're going to eliminate it. So here, I have two equations, right? A nice system. And I'm noticing that if I could solve for one of them, right? But I'm going to be getting into some fractions again, and it doesn't look like it's going to be very helpful. So instead, what I'm going to do is I'm going to take a look at this. Take a look at these y's right here. Plus 3y minus 3y. If I add those together, what's going to happen? If I add positive 3y plus 3y plus negative 3y, what's going to happen? Well, that's going to equal 0y, or basically y is going to be eliminated, and that's what we're looking for in this system, and a way to eliminate some of these variables. So let's go ahead and do that. We're going to add those together. We're going to eliminate it. Now, unfortunately, or not unfortunately, but when I add just the y's, I'm changing the equation. So what I want to do is add everything. I want to add each one going down. So I'm going to add the x's together. I'm going to add the y's together. I'm going to add the constants together, and I got to make sure they're in that order so I can actually do this. But let's go ahead and do that. So 2x plus 6 plus 4 what? Blah. 2x plus 4x is 6x. We already talked about the fact that 3y plus negative 3y is going to give us 0y. And negative 6 plus 6 is going to give us 0. Alright, this 0y, no longer important, right? No longer important. The fact that the constants also kind of eliminated out is just a happy coincidence. If one or more, if the whole thing, we're going to talk about what happens if the whole thing cancels out. That was just a case where you had no solution, right? Where they were in fact the same equation if they cancel out like that. But here, that's just a happy solution where they both canceled out. So what we're left with is one variable. 6x is equal to 0. And again, that's our purpose, right? So whether it's substitution or elimination, you're trying to get down to one variable so you can solve that. We'll divide by 6 to both sides, perfectly legal as long as we're not dividing by 0. Therefore, we get x is equal to 0. All right. We found one of the variables. So far, our ordered pair, our answer, is 0 comma something. Now we'll go back, we'll take the 0, and we can use either one we like. Just like in the last problem, we do not have to use something that is solved. We just need to have something that has a y in it, right? An x and a y. So we can use either one. I think I'm going to use the second one. I'm going to use the second one. So 4x minus 3y equals 6. So let's plug in our 0. I know that x is equal to 0 now. And so this cancels out. I'm left with negative 3y is equal to 6. Or divide by negative 3, you get y is equal to negative 2. And there's my other answer. Alright, we have found our ordered pair via elimination. So what we did was we noticed that those y's would cancel out when we added them. So we added them together. We got 6x equals 0. and therefore x equals 0. And then we plugged it back in to solve for x of -2, and we found our ordered pair. If you forgot what we've done here, the steps are conveniently listed here for you. Let's go try another one. Let's try another one. All right, it looks like, let's go ahead and add these together. So let's add them. We're going to be super careful about that, right? We add. We're not going to subtract. You never subtract. So if you're thinking these x's are going to cancel, you're wrong, right? Because you have 1x plus 1x. You always, always, always add, no matter what. So we have 2x, but then look at this. The y's are going to cancel. Y plus -y is going to be 0y, so they go away, and we end up with 10 on the other side. Now we end up with a nice easy equation. 2x equals 10, divide by 2, therefore x equals 5, right? X equals 5. Well, that was very, very simple, right? So we got the first half. But what else do I need? Instead of just leaving it like that, I have to go back and now I have to find the y, right? And I can use either one. I think I'll use, why not use the first one? I'll use the first one. X plus y equals 6. And I know x equal to 5. So 5 plus y equals 6. Subtract 5 from both sides. Or think about it logically. What plus 5 equals 6? Y is equal to 1. And therefore we get 5, 1 as our solution. I know I'm boxing the x and the y as we go across. You do not need to do that, but you do need to show me the ordered pair at the very end. That is your solution. That is your answer, right? That is the place where these two equations cross. I don't care that x is 5. I care that they cross at 5, 1, right? I'm just boxing it so that we can, it's nice and easy to find later on. Alrighty. Let's try a few more. This next problem has a little bit of an issue with it, right? Kind of like how substitution is awesome if one is already solved for a value, right? Sometimes elimination is awesome because they already cancel out. Other times it's not so awesome. If we look at these and we add them all, we're going to get 7x squared plus y equals 17, and we still have two variables. That's a problem, right? We need one variable. So in order to fix that, what you can do is multiply by anything you need. You can multiply any equation by a factor. So multiply by a factor. And you can do it to both if necessary, to an equation. Multiply anything you need so that these guys will cancel out. And sometimes that takes a little bit of practice, right? But let's try this one. So we're going to try, I'm going to try and eliminate the y's. I think I'm going to try and eliminate the y's. Since one's already negative, I don't need to multiply by a negative. But let's try and eliminate the y's. So I've got negative 2y and 3y. So I've got negative 2y and 3y. What do I need to multiply so that ends up being, excuse me, I have hiccups, is equal to 0, right? So that's my question. What do I need to multiply these guys by so that they end up canceling out? Well, if I multiply the first one by 3 and the second one by 2, then I end up getting negative 6y and positive 6y. So that's what I need to multiply by. It looks like I do need to multiply both of these guys, and that's okay. So I'm going to multiply the first one by 3 and the second one by 2. That's what I'm going to do. So I'm going to go back here now. When I multiply, I actually have to do it to the whole equation. So I'm going to multiply this guy by 3 and this guy by 2. And we're going to rewrite these down here. So the first equation, you know what, let's use some colors. So I'm going to multiply this second guy by 2, just so we can keep track of what we're doing. So this first one in blue is going to end up being 15x, not 5x, because I'm multiplying 3 to everybody, minus 6y is equal to 12, right? So I've multiplied 3 into every single coefficient, every single term. I'm going to do the same thing with 2 now, to the second equation. I end up with 4x plus 6y is equal to 26, and that's what I end up with. Now I can see that if I add these two together, those y's are going to eliminate. So let's go ahead and also do that. Add these guys together. 15 plus 4 is going to be a 19x. We already talked about the y's eliminating, and over here we get equal to 38. Yes, the numbers are getting a little big. That doesn't mean anything's gone wrong yet, because if I divide by 19, I see that x is equal to 2. Awesome. Big numbers don't mean anything. The only thing about them is they are big. They still have all the same rules as every other number. If it's 2, 4, or 565, you can divide by a real number, right? So it doesn't matter if it's a big number. You may be on the right track. Some of these get as high as the 300s, right? The 400s, the 500s. But usually they whittle down to about stuff like 2, or I think the max I've ever seen a coordinate pair was 38, 46. And it's not a big deal, right? It just means that it's a little farther out on the graph. But in this case, our x is equal to 2. So we'll write the first half of our coordinate pair down, which is awesome. And then we can take that and go back to either one of these two equations or even these two equations. They're all the same thing. So any one of these would give us the same y. But I think I'm going to go with something kind of simple. Let's do the first one. So let's plug into the first one. 5x minus 2y equals 4. I now know that x equals 2. So 5 times 2 minus 2y equals 4. In other words, 10 minus 2y equals 4. Subtract that 10 over, you get negative 2y equals negative 6, or y equals negative 3. Nope, I'm sorry, y equals positive 3. Alrighty, so that means the other half is 3. We get an equation, a coordinate pair of 2, 3. Alrighty. I've got another one here for you that I would like you to try out on your own. Try it out. 3x minus 9y equals negative 18. 2x plus 4y equals 18. It looks like you're going to have to do some multiplying, possibly to both, if not just one. And then you're going to solve for both your x and your y value to get the coordinate pair. Go ahead and pause the video now and try it out yourself. Okay, so I hope you had a chance to try this out. I'm going to kind of just section it off here. And then we're going to kind of, yeah, okay, cool. So I've got 3x plus 9y equals negative 18, and 2x plus 4y equals positive 18. Let's work with orange. I'm going to I think I'm going to eliminate, I'm going to eliminate x this time because they're a little smaller. I'm going to multiply this one by negative 2. And this one by positive 3. That way one of them will be negative and one of them will be positive. So let's do that over here. First one becomes negative 6x. Let's see, that's plus 18y. Equals 2 times 18 would be 36. It's positive because negative times negative. In the second one we have 6x plus 12y. Equals 3 times 18, I believe it is 54. Yes, it's 54. So they're both positive, we end up with a positive 54. Alrighty, and then I'll add these two together. So all I did was multiply negative 2 into everybody in the first equation and 3 everybody in the second equation. You may have chosen a different route. You and I should end up with the same answer. So just because you didn't choose to multiply by negative 2 and 3 does not mean you're necessarily wrong. If you chose to eliminate the y's, you might have gotten 2 different equations, but we should end up with the same coordinate pair. So don't go ahead and don't erase anything you have yet. Alright, I'll add these two together. The x's cancel. I end up with 30y equals, I believe, 90. Yep, 90. Or y equals 3. And there's my first half. Now I'll take that y equals 3, I'll go substitute it back. I think I'll substitute in the second one. 2x plus 4y equals 18. And I know that y is now equal to 3, so 2x plus 4 times 3 is equal to 18. 2x plus 12 is equal to 18. I'm losing room, so I'm going to go over here. 2x is equal to 6 because I subtract that 12 to the other side, or x is equal to 3. And so my final coordinate pair is x is 3, y is 3, 3, 3. Awesome. All right, so that is elimination. Elimination eliminates one of the variables, right? Just like substitution substitutes one of the variables away. But in both of them, you get rid of a variable so that you can solve for one of them, and then you go back, you find that variable you got rid of when you plug it back in. Alrighty. We've got a couple more things to talk about. And elimination. I'm going to pause just for a sec. No, I'm not. I just have to check one thing real fast. Canvas, leave. Yes, so I believe this is where I stopped for your homework. We're going to come back to the other parts later. And we're going to pick up where we left off next time. I'm going to keep these ones for next time, though, so solving by any method. On your homework, though, remember, you will have to choose between substitution and elimination. All right.